Hey everyone, welcome to Insights by Harish. In this video, we will study about linear regression in depth. We'll start with some introduction and aim, some key terminologies that are required to understand the basic concepts of linear regression, its types, evaluation metrics, which are also called as cost function, a gradient descent, which is an optimization technique, some assumptions that we make while performing the linear regression tasks, and implementation. So beginning with linear regression is a kind of supervised machine learning algorithm. The supervised machine learning algorithm are of two types, regression and classification. So the basic difference between both of them is in regression task, the outcome you have continuous values, while in classification task, in outcome you have categorical values. Let us understand one example. Let us consider that we have a data set. We have a data set in which we have to predict the temperature for tomorrow. So we have the wind, whether it is cloudy or not, then the humidity, and based upon all of this we have to predict the temperature for tomorrow. Now the value of temperature will differ for every instance depending upon its input feature. For some it will be 3 degrees Celsius, for some it will be 40 degrees Celsius, for some of them it will be minus 1 degree Celsius. So here the temperature value differs for every instance depending upon its input features. So this is what we have a continuous values. So this is a regression task in which the outcome, in this outcome variable, we are having the continuous values. While in classification task, you have categorical outcomes. Let us consider that you have all this data set and you have to predict whether it will rain tomorrow or not. Now you have whether it is windy or not, cloudy or not, humidity, and from this you have to predict whether it will rain tomorrow or not. Now the answer for this will be either yes or no, that either it will rain tomorrow or it won't. So the output of this is categorical, either yes or no, and nothing apart from that. So this is a kind of classification task. It can be either yes, no, true, false, 1, 0, and then can be multi-class classification as well, where you have more than two categories. So in this video we will be studying about a linear regression where our outcome will have continuous values. So beginning with, in linear regression we consider that there is a linear relationship between the x-axis and y-axis, between our x variable and y variable. This is a x and consider this is a y. Now this x is an independent variable. This x is an independent variable, which means it is not dependent on any feature. X is independent. It is what is given to us. So it is an independent one. Well, y is a dependent variable, which means it depends upon the input features. It will change as per the input features. So y is a dependent variable and x is an independent variable. And in linear regression, we assume that there is a linear relationship between this independent variable and dependent variable. Linear relationship means as the value on x increases, the value on y also increases. So let us consider this. Let's say for this point, this is the value on x. Well, this is the value on y. Now, as the value on x increases for this point, the value on x increases. Let's say this was 2. So this might have become 4. So as the value on x is increasing, the value on y also increases. Let's say this also increased. So for this variable, the value on x increased, the value on y also increased. So this is a linear relationship. Of course, we have some variables where this won't be applicable. Let's consider this one. For this, the value on x is increasing, but the value on y isn't increasing. So such kind of points are called as outliers, where they differ from the standard format, where they do not follow the standardized techniques or standardized patterns. So such kind of data points are called as outliers, and we have outliers in all data sets available. So, but maximum data points follow the linear relationship pattern. Like if the value on x is increasing, the value on y is also increasing. And that's the basic foundation of linear regression that we follow, that there is a linear relationship between our independent variable and dependent variable. For example, consider this example. Here on x-axis we have study hours and on y-axis we have marks. Now as the study hours increases, as we start studying for more and more hours, the marks also increases. So this is a dependent variable and this is your independent variable. As your independent variable, that is the number of hours you study, is increasing, your marks, that is your dependent variable, is also increasing. That is, your marks are directly dependent on your study hours. So this is a kind of linear regression where there is a linear relationship. When one input variable is increasing, the dependent variable is also increasing. So the main thing that we do in this linear regression is to draw this line. This is a line. Initially, when we plot the lines, we have to draw the line that passes as close as possible from all these points. Of course, we don't have the perfect data that this line cannot pass through all the data points. What we have to do, we have to draw such a line that will have minimum distance from all these points. This distance from this point to this line should be minimum. So we need to draw such a line that the distance between this point to this line is minimum, applicable to all the data points. So moving forward, here as we can see, the equation of this line is y is equal to mx plus c, which is a basic mathematical equation. Now the m stands for slope and c stands for y-intercept. In machine learning, we consider our slope as weight and our y-intercept as bias. So let us consider this is a graph and this is our line. So the angle it is making is a slope. The angle that it is making here is your slope m, while the distance from origin up to that line is our y-intercept c, and this is your m. So this m is a slope, that is the angle it is making, and c is the y-intercept. In machine learning, m is weight and c is bias, while x is your input variable. Now, as you know, as we change this m and c, the line will also change. In this equation, if you write it in the terms of weight and bias, your y will equal to w x plus, so in this terms we can see x is a fixed value, x is your input value which is fixed, so you cannot change this. What you can change is your weight and b. So as you change your weight and b, the line will also change. Like here this is a slope, if I increase the slope, the line will change. I have increased the slope here. If I increase the slope more, it will increase more. If I change the y-intercept, the line can start from here. So as I am changing these features w and b, the line is also changing. So when I say that we have to draw a line that passes as close as possible from all of these points, there can be multiple lines. This can be a line, this can be a line, and this can be a line. So which line to choose? There can be multiple lines. So this line changes depending upon the values of weights and bias. As the values of weight and bias, that is this m and c, changes, the line also changes. So which line to choose depends upon the distance between the points and the line. You have to choose a line that has minimum distance from this point to line. Minimum distance from this point to line. And that's how we compute error as well, which we'll study later in this video. So that's the basic understanding. Now we know that as we are changing the weight and bias, this line is changing, and we have to find such a line that is having a minimum distance from all of these points. So the main aim of our linear regression is to find such a weight and bias that our best fit line, this line is called as best fit line. We'll understand what it means. So to find such a weight and bias that our best fit line will minimize the error and increase the accuracy. What do you mean by best fit line? See, in this case, you know, the line is passing from all the data points. It is passing through all the available data points, and such a line is called as perfectly fit line. While in this case, where the line cannot pass through all the data points, but it at least tries to pass as close as possible from all the data points, and such a line is called as best fit line. When you have a perfectly linear data, that perfect linear relationship when you have between your x-axis and y-axis, the data is in this format. But you rarely get such kind of data in real-time environment where you have a perfectly fit line. Most of the time you have such a data where, though it is in a linear fashion, but it is scattered somewhere here and there. So the line that cannot pass exactly from all data points, but it tries to pass at least as close as possible from all the available data points, is called as best fit line. So here our main aim is to find such a value of weight and bias that it will plot a best fit line which will have the minimum distance from all of these points. Now, what's the significance of this weight and bias? Understanding that, firstly, weight. Now, weight signifies the impact of input on our outcome. See, when you have multiple input features, your output, it depends on the input features, but every input will have different impact on your output. Let's consider this example. In this example, you have to predict the insurance charges depending upon the age and hobby of a person. So here you have two features, age and hobby, and depending upon which you have to predict this insurance charges. Now, every column, every feature has a weight associated with it. Let's say W1 is the age associated with weight associated with age column, W2 is the weight associated with hobby column, and you have to predict this insurance charge. Now age is an important factor in determining the insurance charge, but the hobby isn't an important factor. You cannot predict the insurance charge depending upon a person's hobby. So the age is an important factor in deciding the charge, while hobby isn't. Now, as a human, we can understand this by observation, but for the machine, we need to plot it in a numerical fashion. Let's say the weight associated with this age column W1 is 0.8. While the weight associated with this hobby column is 0.2. Now here we can clearly see that the weight 1, which is the weight associated with age column, is greater than the weight associated with hobby column. So here we can conclude from this observation, we can conclude that the age column has higher impact on our target variable, that is on our outcome insurance charge, rather than hobby. So the input feature that has higher weight has high impact on target variable, while the input feature that has lower weight has less impact on our input feature. So that was the significance of weight, which helps us to understand the impact of an input on the outcome. While the bias. Now the bias again has an important role to play. Let us consider that we have an equation without bias. Let us consider the equation without bias. We have y is equal to wx, and we are assuming that we don't have any bias. Now this weights and bias are initialized by our model, our machine, our library, scikit-learn. So let us consider that if in case the weight is initialized to 0, if our model initializes the weight to be 0, in that case the whole element will become 0, because anything multiplied by 0 is 0. So in such case, though it is a rare case, but it can happen that if the weight is initialized to 0, in such case your whole element will tend to 0. So to prevent this from happening, you add a non-zero term bias into it. Now what will happen? Though your weight is 0, but still your y won't become 0 because it has some non-zero value b. So to prevent the element from turning to 0, you add bias. So bias is an important factor that prevents your element from turning to 0. Now that we have understood all the key terminologies, we'll move ahead to the types of linear regression. So we have two types of linear regression. We have many types of linear regression, but the most popular one are simple linear regression and multiple linear regression. So in simple linear regression, we have only one input feature, and our outcome, that is our target variable, is dependent on a single input feature. Now here you can say we are predicting the insurance charge depending only upon age. We can input the age and the model will predict the insurance charge. So in simple linear regression, we have only one input feature and we are predicting depending upon only that single input feature. So in that case, we have a simple line equation which is y is equal to wx plus b, where your y is your insurance charge at I, which you are going to predict. W and B are the terms that your model, your library will generate depending upon the iterations and trial and error. And X is the input age at I. Now, if you consider row 1, if you consider this row 1, here the charge at 1 will be equal to weight into the input 1, that is 35 plus B. Same for row 2 and row 3. Now, in multiple linear regression, you can have multiple input features. Like in simple linear regression, we had just a single input feature. While in multiple linear regression, you can have n number of input features, and your target variable, your outcome, will depend on that n input features. Now, for example, here I have considered two input features, age and hobby, and I am predicting insurance charge based upon these two input features. So in this case, the simple line equation is extended. Like the normal equation that we had was y is equal to w into x plus b. This was a simple line equation that we had in a simple linear regression. Now, in multiple linear regression, we expand it to n number of points. Let's say for point 1, that is for input 1, it will be w1 x1. For input 2, it will be w2 x2. Like this, up to nth point, it will be w1 xn and plus bias term. So in this case, you can see that w1, w2 and b are all these factors that will be generated by our library, generated by our model itself, depending upon the trial and error and iterations. So that's the basic difference between simple linear regression and multiple linear regression. Now, moving forward, let us understand the cost functions. Cost functions are basically used to evaluate your model. You have to see how much error your model is reporting and how much accurate your model is. There are multiple types of cost functions that we have in linear regression. Let's start with some basics first. Now, you can see here, this is your actual data point. For an example, I've considered here only a single data point. This is the actual data point. You will map that data point onto your best fit line. This best fit line is also called as regression line. So you will map that your actual data point on your regression line. So this is our actual data point, which is symbolized with y, and this is our predicted data point, which is symbolized with y hat. So the actual data point is symbolized with y, and when you map that data point onto this regression line, it is symbolized with y hat, and the distance between both of them is symbolized with d. Now when you have to find this d is the difference of actual data point and predicted data point. So the formula for d is this actual data point, which is y, minus predicted data point, which is y hat, and d is the difference between both of them. Let's say that the value of your data point is 5 and the model predicted it to be 3. Then your distance, your d, will be 2, that is 5 minus 3, 2. So the first cost function that we have in linear regression is mean squared error, MSE. So as in a previous slide, we took the difference of only single data point for an example. Similarly, you have multiple data points and you have to take the difference between them of every data point. You have to take the distance from first data point to the regression line. So you have to do this for all n data points. You have to take the difference between data point and the regression line for all the available data points. Let's say d1 is the distance between the first data point onto its predicted one. d2 is the distance from the second data point onto its predicted one. So in such a way, you take the distance for all the data points and you add them up. So starting with d1 up to dn, you add all the distance starting from the first data point up to nth data point. Now, as in a previous slide, we studied that the formula for d is the value of actual data point minus the value of your predicted data point, which is y hat. So this was for a single variable. Now we can expand this equation. For d1 we can write it as y1 minus y1 hat, plus for d2 we can write it as y2 minus y2 hat. Up to nth point is yn minus yn hat. Now in some cases it can happen that the predicted value is greater than the actual value. Let us consider that our model predicted a value to be 5. And let's say the actual value, this y value is 2. In that case, your predicted value is greater than your actual value. Then in such cases, it can happen that you may get a negative value. Now for this element, if the predicted value is greater than your actual value, then the answer you will get will be a negative value. So to prevent this negatives, you square it up. You take the square of y1 minus y1 hat up to nth data point. So you are squaring it up to prevent the negative data values. Now we can generalize it. Now this is our equation and we will write it in a generalized form, which is this. So summation of I is equal to 1 up to n yi minus yi hat square, where I can start from 1 up to n. This is a generalized form, and this generalized equation is called as sum of squared errors. This generalized equation is called as sum of squared errors. And when you divide the sum of squared errors with total number of data points, that is n, let's say n is total number of data points that you have. When you divide the whole sum of squared error with the total number of data points, you get mean squared error. This is your mean squared error. It is 1 by n, summation of I is equal to 1 to n, yi minus yi hat square. So this was the first cost function that we have, first evaluation metric, mean squared error. The second one is mean absolute error. Mean absolute error is very similar to mean squared error. The only difference is that in mean squared error, to prevent this negative values, to prevent this element tending to some negative value, we took the square of it. But in mean absolute error, what you are going to do is, you take the absolute, you take the modulus of that element. In order to prevent the negative values, instead of squaring it up, you take the absolute, you take the modulus of that element, absolute values. And then the whole equation is same up to nth element. Then you take a generalized form of it and you divide it, the whole this equation with a total number of data points, that is n, and you get your mean absolute error. So it is very similar to mean squared error. Only difference is here you have modulus and there you have square. The third cost function is root mean square error. In root mean squared error, you take the root of mean squared error. Now this is your mean squared error, and when you take the root of it, it will be root mean squared error. So this was your third cost function. There are more. There is R2 score, adjusted R2 score, but we just studied the popular ones and most frequently used ones. So moving to an important topic, which is gradient descent for linear regression. Now, what is gradient descent? Basically, this is a kind of parabola we have, and the gradient descent is an optimization strategy. Now, what is an optimization strategy? Here, you know that we have to plot a best fit line such that it will minimize the distance from the data points. So, this best fit line will change its position depending upon the weight and bias. So here we have to find the best fit line depending upon the weight and bias. So which means we are optimizing the values of weight and bias until we get the perfect best fit line. So here we are optimizing the weights and biases, for which we require the understanding of gradient descent. Now let's say first you have found, let's consider the mean squared error metric, mean squared error cost function, and when you computed the error, you are somewhere here. You are somewhere here. In gradient descent, your ultimate goal is to reach here at this point, which is called as global minima. In gradient descent, your ultimate goal is to reach this global minima. No matter where you are, you can be here, you can be somewhere here, but your ultimate goal is to somehow reach here, because at this point your error is zero, error is minimum. Gradient descent, when you plot it in such a way, in a U shape, your ultimate goal is to minimize the error, which means to reach at this global minima to reduce the error. This is the formula for weight updation. Now see, first your model considered some weight. Let's say the weight was W1, and it considered some bias B1. Then it plotted the best fit line. Then the model again started for second iteration, in which it considered different weight W2 and different bias as well, which is B2. So it will continue it up to some finite iterations, and then it will choose the weight and bias that is plotting your best fit line, which is minimizing the distance between the data points and the line. So in this case, this is the formula you can see. Your new weight will be your W, it is your old weight. This is your old weight. So your W new will equal to W old minus alpha into, this is the gradient of loss function. Gradient of loss function, L is the loss function, that is mean squared error, mean absolute error. This is the gradient of loss function with respect to change in weight. Now computing this is again using some chain rule, but we won't study this because that is out of scope of our video. So this is the gradient of loss function with respect to change in weight, and alpha is the learning rate. Now learning rate, it determines how fast or slow we move to reach this global minima. Our ultimate goal is to reach this point, but it depends upon our speed. It depends how fast or slow we are moving towards this point. Let us understand that. Let's say this is the your gradient descent, and your ultimate goal is to reach at this point. Let us consider that you are having very small learning rate. Let's say your learning rate is alpha 1, which is very small. The learning rate is very small, which means you will take very small steps to reach this point. Very small steps. And eventually you will reach here. But as you are taking very small steps to reach this point, this is a very slow process, and in which this means that your model is learning very slowly. So now you will consider some new learning rate which is very large. Let's just say that now we are considering some learning rate alpha 2, and this alpha 2 is very large. Let's say it is very large than your previous learning rate, that is alpha 1. Now in this case, as our second learning rate is very large than the previous one, it will take very large steps to reach this global minima, due to which what will happen, it will overshoot the condition. That is, this is a step. Next step it will take here, then from here to here, then again from here to here, here to here, again from here to here. So this means it is just moving from here to here, but it isn't actually reaching this global minima. It is overshooting the condition. So when your learning rate is too large, that is, the steps taken to move towards this global minima is too large, you overshoot the condition. So from both of this, we came to a conclusion that we do not require a very small learning rate and we don't require a very large learning rate. The learning rate should be adaptive. What do you mean by adaptive? Adaptive means it will change depending upon the situation. Now let's say this is the gradient descent that we have. Now we have to reach here. So we have to find such a adaptive learning rate, which means initially it will take larger steps. Initially it will take larger steps. But as you approach to this global minima, the learning rate will be reduced. Now it will start taking smaller steps in order to prevent overshooting the destination. So this is the adaptive learning rate, in which initially you are taking larger steps, that is, your learning rate is large initially, and as you are approaching this global minima, you reduce this learning rate where you take small steps in order to reach the global minima without overshooting the condition. So that's the importance of a learning rate. Now same formula is applicable for bias as well. Your new bias is equal to old bias minus learning rate into the gradient of loss with respect to change in bias. Now we won't go into detail of this formulas because that will be out of the scope of this video. But these are the formulas that we use to optimize the weights and biases in order to reach this global minima. And there are two cases here. Let us say that initially when you computed your cost function, your mean squared error, you are somewhere at this point, which means now you have to minimize your cost error and you have to reach it at this global minima. So at this point, your slope is negative. You draw the tangent, you draw this tangent, and when you take the slope, it is a negative slope, as I have drawn here. You draw a tangent at that point and you take the slope, which is a negative slope. When you plot that onto this x-axis, this is where you are. Now in order to reach the global minima, you have to move in a forward direction here. While in a second condition, let's say that you computed your mean squared error and you are somewhere here. Now in order to reach the global minima, here you have to move backwards, because when you will take a tangent here, this tangent, and when you will compute the slope, it will be a positive slope. Now when you plot that line on your x-axis, you have to move backwards in order to reach this global minima. So these are the two cases of gradient descent here. This was the basics of gradient descent in linear regression. So gradient descent is in short, it is a strategy to optimize your weights and bias, optimize your loss. Here you are optimizing your features, this weights and bias, in order to reach this global minima, which means you are trying to reduce the error and increasing the accuracy of the model. Now let us understand the assumptions in linear regression. While performing the linear regression task, we assume some things, and that are, the first one is linear relationship between dependent and independent variable. As I said at the initial stage, that we assume that as the value on the x is increasing, the value on the y also increases. That is, when your number of hours you study increases, your marks also increases. So that's a linear relationship, while this is a non-linear relationship. And we are assuming that our data is following this linear relationship while performing the linear regression. The second assumption that we make is independence of data. By independence of data, I mean is like here, the data points aren't dependent on any other, on each other. Here, every data point is independent from every other data point. While in dependent data point, your current data point is dependent on its previous data. Let us consider the example of patient. Now, the patient's today's data, that is his how well he have recovered, how he is doing, will be dependent on his previous data. That is the medication that he took yesterday, the treatment that he took yesterday. Depending upon that yesterday's data, his today's health will be decided. So here your data is dependent on the previous data as well, which is the time series data, and such a data is called as dependent data. So while performing linear regression, we assume that our data is independent. That is, there is no multicollinearity, and every data point is independent from every other data point. The third assumption that we are making is our data is normally distributed. This is a normal distribution, which is also called as Gaussian distribution, and this is not a normal distribution. This is in this you can see the distribution is somewhat like this. And you reach here, from here to here, and then again from here to here. So this is not a normal distribution. While your normal distribution is always in this fashion, it increases at some point and it again decreases. So in linear regression, we assume that our data is normally distributed in this way. Now, as we have covered all the concepts of linear regression, we will see some implementation. For implementing linear regression, we will be having this data set where you have this input and you have to predict the insurance charge. So in input you have the age of a person, the sex, that is the gender of a person, the body mass index, the number of children he or her they have, a smoker, and the region feature. And depending upon all these input features, you have to predict the insurance charge for that person. This is the example of multiple linear regression where you are having multiple input features. So let's start coding. So let's start with coding. We will import the pandas library and we'll import warnings to ignore the warnings that the Jupyter Lab gives us. Now let us load the dataset. Insurance DF is a data frame in which we'll load the dataset. This is the path on which the dataset on which the CSV file is stored. Let's display it. This is our dataset. You have age, sex, BMI, children, smoker, region, and depending upon all these input features, so you have to predict these charges. We'll start with data cleaning. Let's check whether it has any null inputs or empty values. As you can see here, we don't have any null inputs, so we can directly start with data processing. Now in this data set, as you can see, there are some categorical features like sex, region, smoker. These are the string values, these are the categorical features, and machine learning cannot handle such features. Machine learning only requires the values in numerical format, so we need to convert these features into numerical format. Let's start doing that. Let us take all the categorical features. Let's display it. Here you can see these are the three features that contains the categorical values. Now we will convert these categorical values into numerical ones using the sklearn library one hot encoder. So let's import that. We will create an object of that. Encoder is an object of one hot encoder module. Parse is false, and we'll ignore the unknown values. So handle unknown, ignore. Now we will fit this categorical features into this encoder. Encoder.fit the categorical features of this insurance data frame. So now we have successfully fitted. Now that we are creating new columns with the numerical attributes, we need new column names for it. For that, what we'll do is we'll create encoded calls. We will use the function of an one hot encoder, which is get feature names out from categorical columns. Let's check. So these are the new column names that we will insert it in our data frame. So it created a new column for every attribute like female, male, no, yes, and it will consist of values in a combination of zeros and ones. Let's add this into our data frame. Let's check our data frame. So this is the data frame. The new columns are added. Every attribute has turned into a new feature. So now we don't require this original categorical column, so we'll delete them. We don't require this text column, then smoker and region. In place true is used to make the changes permanent changes. If you don't use them, the changes will be temporary. Let's display it. So now we don't have this categorical column. All the data that we have is in a numerical fashion. Now as we can see, every column is on a different scale. Let's check this. When you check the age column, the minimum value is 80 and the maximum value is 64. For children, the minimum value is 0, maximum is 5. For charges, it is 1000 up to 63,000. So for every column, the scale is different. So before training the model, we need to bring the scale of all this column onto one standard scale. And we will do that using the min-max scalar library, which is used for data normalization. So from sklearn.preprocessing, we will import min-max scalar, creating the object of min-max scalar, which is this is an object of min-max scalar module, and we will fit our entire data frame into it. Okay, before doing this, let us divide the data frame into the input features and the target column. Let's say X is our input feature. And the target feature will be the charge. As you can see, this will be our input. Here we don't have the charge variable. The charge feature is our target feature. Here we don't have that. We are going to predict that. Now we will scale the whole input data using the min-max scalar. The min-max scalar basically scales it between 0 to 1. We'll fit it into the input one. Now let's transform it. Now when you display, see, here the data was on different scale for every column. Here for every column the data is between 0 to 1. So that we have scaled it between 0 to 1 using the min-max scalar library. Now that you have scaled, we will do the trend test split. Basically, we are dividing this data set into some training set and a testing set. Input data set, feature, and test size. Test size is 0.2, which means 80% data will be into the training set and 20% data will be into the testing set. And random set is 42, which means we will get same data for every iteration. Let's check the shape of that. As you can see, in total we had 1338 rows, out of which 1070 are in training set and 268 are in testing set. Now let's train the model. So from sklearn.linear model, we will import linear regression and creating the model, that is an object of linear regression class. We'll fit it into our xtrain and ytrain, that is our training data set. So we'll fit this training and testing data sets. sorry, training input and training target data set. Now let's do some prediction. Let's pass this testing data set. So, okay, what were the actual values for this? The actual values were stored in the test data set, y test. These are the actual values. Let us store this into some y predicted. These are actual values. And let's check the predicted values. Let's check only the first 5 values. So the actual value was 9095 and our model predicted it to be 9024. Here the actual value was 5272. Model predicted it to be 7260. So it is closed. Now let's evaluate the model. So we'll import the mean squared error and root mean squared error. So we can import mean squared error as well as mean absolute error. We will pass the training set. We'll pass the actual values and the predicted values. This is a mean absolute error. Let's do the same for mean squared error. This is our mean squared error. Now for root mean square error, we do not have any library for that. We need to do that manually. We'll import NumPy. And we'll take the square root of this mean squared error. So NumPy dot square root of this mean squared error. So this is our root mean squared error. Now you can do some trials and errors, some regularization, some optimization to reduce these values. By reducing these values, what I mean is to reach the global minima. So that's it for the video. Thank you for watching.